Calorimetry is talking about measurement and how heat changes from one thing to another. There's a couple of different types of calorimeters. I think if you take Physics 2, Ms. Rademacher has fancy calorimeters that are called bond calorimeters, where you keep a constant volume throughout. I do not use her fancy calorimeters. Her fancy calorimeters have what's called a heat capacity of their own that you have to use within your calculations. Another reason why I don't want to use it. Primarily, I don't want to use it because anything that I have seen from the College Board about what type of calorimetry questions you have deal with styrofoam cup calorimeters. So that's what we're going to be using. This would be under constant pressure, room pressure. So it's a constant pressure calorimeter. So again, calorimeter should be a closed container to measure heat change. You may recall your calorimeter from Chem 1, but now I have added this very fancy piece of equipment to make it more closed. We only use this in AP Chem, folks, because this is really fancy stuff. I even poked a hole in it so then your thermometer can fit into it. So this is our calorimeter. It's athletic tape around the outside that I used. So again, we use a styrofoam cup calorimeter as our closed container, but same type of idea of we're measuring heat exchange that's happening. Now, very common, we have water inside of here. So what we do is we measure the change that water undergoes. And then with that, based upon the conservation of energy law, first law of thermodynamics, if the water gained a certain amount of energy, whatever we put in it lost that energy, or vice versa. So that's how we're able to do our math, but that's where, in particular, the positive and negative sign play a role in what we're going to be doing. Because too often when we do lab activities, students forget to switch the sign. They solve for how much energy the water gains, but then they use that value, not the negative value, for the other object that we're actually trying to look at. So usually the water is more of our surroundings, and the system is whatever we're putting in it. Now, this slide is going to go over a couple of terms for you to be aware of. There is a difference between specific heat and heat capacity. And I sometimes use the terms interchangeably. So I apologize for that. Or it's called the specific heat capacity. Specific heat is that lowercase c value that we used in Chem 1. Remember we talked about things like put your hand on your desk top versus your desk leg. The desk leg feels colder than the desk top. And if you don't believe me, you can even feel that for yourself. However, they're at the exact same temperature because they're in the same room. And anything that sits in this room long enough will be the same temperature. So why does the leg feel colder? It has a lower heat capacity, which means it can absorb the heat from your hand really quick. That's why things feel cold. You lose heat. You put ice in your hand, it feels cold because the heat from your hand is going into the ice. So the specific heat capacity, that's what that's referring to. That's what we're actually going to be doing in the lab today. And you did a lab very similar to this in Chem 1. But like I said at the start of class today, this is kind of a review day for Chem 1. Again, I'm not trying to get too far ahead. I think we could have tacked in a little bit more material today, but I kind of like just doing one new type of math at a time each day with you guys. Heat capacity, capital C, I don't think you're going to see very often. But I want to make sure, just in case it's brought up, that you are aware. This is going to take into account not only how well this substance absorbs energy, but its mass as well immediately. So I referenced on slide number 1 how Ms. Rademacher has these special kinds of calorimeters. They have their own heat capacity, capital C value that you have to take into account when you do any of your math. We don't do that with our styrofoam cups. We consider our cups to be insulators, not conductors. Metals are good conductors of heat and electricity. Some other things, in particular, your things that are made with covalent long molecules, are going to be better at insulating. Very simple question I have on the bottom of the page could talk about an iron bar. And if I was to cool it, I could calculate how much energy was released. The primary equation, and I apologize, this shouldn't actually be a negative sign. This is after a dot, they do a dash. The primary equation that we have to know in our thermodynamics for this day is Q equals mc delta T. Where Q stands for heat, M stands for mass, C is the specific heat capacity, so that's a lowercase c. It's the more common way that you're going to see it. And delta T, remember that triangle is delta. Delta T is your change in temperature, the final temperature minus the initial. Again, the reason why I wrote that second equation on there is heat capacity, capital C, takes into account both the mass and the specific heat capacity all at once. But like I said before, I primarily avoid that because I don't believe the College Board will do much with that either. But there is a slight difference between those two, so I wanted you to be aware of it. So what I would actually say is equation-wise, why not? The two equations in bold are the ones that you're going to be using today. Q equals N times H. Remember, N stands for your number of moles. This lowercase n is used on your equation sheet for the number of moles in a couple of different equations. H stands for the enthalpy or the heat of fusion or heat of vaporization. And again, I'll go over the use of this on a practice problem on the next slide. The second equation in bold is the one that is given to you on your equation sheet. Q equals mc delta T. And again, I remind you what delta T means then as well. I don't know why they don't give you the first equation, but I know they don't. I don't know if it's worth noting as well, but on the whiteboard, I have written down these different constants for water. On a problem, on a quiz, or a test, you would typically be given these values if you're talking about water. Now, the heat of fusion I've seen as 6.01 as the animation showed to start class. But when I looked it up this morning, it was 6.018 something, so I could round it to 6.02. Again, either or, that's the heat of fusion of water. Heat of vaporization is 40.79 kilojoules per mole. Now, the one number on here of these five that I've written on the whiteboard that you may want to know is the specific heat capacity of liquid water. That's the one that it might be useful to memorize, 4.184, because I know it's not on the equation sheet. You might be given that one on their tests, but for some reason I'm thinking I've recalled looking at tests where they haven't given you that value. Okay, so what I want to do to wrap up notes is I want to go over one question that's somewhat similar to what we did in Chem 1, where we talked about how much energy is involved with either heating or it could be cooling water from one temperature to another. And a reminder that this is a multi-step problem. This is the type of thing that I have seen before on their free response in particular. Typically, simpler calorimetry problems I've seen in multiple choice, but ones that involve multi-step I've seen in their free response. On the bottom right-hand side, so before I start solving this, on the bottom right-hand side of this slide, I have a reminder of the heating curve for water. Again, remember on the heating curve, we have three slopes representing the three states of matter: ice, water, and steam. And then we have two plateaus representing the phase change. This heating curve even does a good job of showing that the second phase change involves more energy than the first. It's a longer plateau. It's actually something we're trying to emphasize more this year in Chem 1. We've been showing them heating cooling curves a lot in Chem 1 versus when you guys did it, because we want to make that point. The energy needed to go from a liquid to a gas is always a greater value than a solid to a liquid. Because remember, when you go from a solid to a liquid, you loosen things up. They're still attracted to each other, but they're no longer in a rigid structure. But when you go from a liquid to a gas, you completely break apart intermolecular forces. Nothing's holding anything together anymore. So that's why we have different numerical values, 6.01, 40.79, to represent those phase changes. Water being hydrogen bonding has a fairly high value for both of those. If you had something with a weaker intermolecular force, it would have lower values for those. Okay, now on to this question. If I had 20 grams of water at 45 degrees Celsius and I heated it to 110, I could calculate how much energy would be required to do all of that. So what I'm going to do is I'm going to switch over to the Smart Notebook and just write out how to solve this problem for you. And again, that wraps up our notes for the day. One of the sheets you picked up on the way in, it's actually a homework assignment I give to Chem 1 to give you practice in this type of stuff. That's something that we could do at the end of the hour if we have time for other things. So I'm just going to rewrite the main data here. To remind you of what the problem was. In Chem 1, by the way, we often told you, why not mark down your temperatures? And the reason why we told that to Chem 1 students is it tells you then that it's a multi-step problem. Step number 1 would be I would have to heat my water from the initial 45 degrees Celsius up to the last temperature water exists as a liquid, 100. Since there's a temperature change, I'm going to use Q equals MC delta T. My mass in this problem is 20 grams. The C value, since I am dealing with liquid water, is 4.184. That's a joules per gram degree Celsius. And then lastly, my delta T for this first part. Final minus initial, 100 minus 45. 5. If I do this first round of multiplication, I would get 4,602 joules. There's a reason why I underlined my zero. Because I should only have 3 sig digs in my answer, but I'm going to save that to the end. Plus, rounding this to 3 sig digs would be kind of weird. I'd have to write in scientific notation. So I'm just going to avoid that for now. Does this ring a bell? So we just got to kind of remind you a little bit more of the next steps to get you where you need to go. But right now, we are at a liquid at 100 degrees Celsius. Step number 2 in this process is I need to turn my liquid into a gas. I need to go across this plateau. There is no temperature change at that step, which is why my step number 2 going to involve that other equation I had in the notes. Moles times the heat of something, depending upon which plateau we're on. Now, this is slightly different than what we did in Chem 1. Because what I did in Chem 1 with these two values I'm pointing to on the whiteboard right now is I converted them to joules per gram for Chem 1 students. That way, all they had to do is take the mass times the heat of fusion or the mass times the heat of vaporization. I tried to make life a little bit easier for them so they wouldn't have to do a kilojoule to joule conversion, so they wouldn't have to do a gram to mole conversion. You will not be given those values in those nice, neat terms. Because typically, just as the video showed, it's reported as a kilojoules per mole. So I need you guys to get used to using that format instead. That's why we're going to do just a little bit extra work here. I have 20.0 grams. I have 1 mole for every 18.02 grams. Okay, I got to pause this for a second. This thing is just out of whack. It's tough writing in one spot and seeing it all showing up in another. Okay, so if Caitlin watches this later, she can watch me adjust the smartboard. Great. So, grams to moles, now I can plug in, since this is the second slope, the heat of vaporization value, which is 40.79 kilojoules per 1 mole. Bless you. That would get me, with 3 sig digs again, 45.3 kilojoules. So once again, what I'm doing is I first calculated how much energy, that's in green, it took to heat up my water that was liquid to 100 degrees Celsius. Q equals mc delta T. Step 2, how much energy is now needed to break the hydrogen bonding, the intermolecular force. Moles times heat of vaporization. My final step is I need to take my gas at 100 degrees Celsius, heat it up to 110. With the temperature change, I'm going back to Q equals mc delta T. The mass is 20 grams no matter what state of matter it is. The C value of steam was given to you on the problem of 1.99 joules per gram degree Celsius. And the delta T in this particular problem, because we are only going up 10 degrees more, is 10 degrees. This gets me 398 joules. In Chem 1, when we first went over this, we'd show you a 5-step problem, every single slope and plateau we could. You're typically not going to see that though in assessment, because as long as they give you at least 2 steps, you've shown that you know that this is a multi-step problem. Why waste time doing 5 steps? Now, what we'd have to do to wrap this up is we'd have to add all of these values. What might help out is to make this all into kilojoules. For example, this is 4.60 kilojoules. Now that third sig dig kind of makes sense for me. I already have 45.3 kilojoules, and this is 0.398 kilojoules. It is not a huge point of emphasis when it comes to significant digits and adding. However, the rule is whatever place they have in common last is what we should be adding to. All 3 of these numbers have a tenths place to them. So that's where we round our final answer. So what I would call kind of Q total for this entire process, I have is 50.3 kilojoules. I don't know why I have a slash there. This isn't the only thermal math that we have to know how to do. For example, in the lab activity today, I'm going to have the packet take you through step by step to show if you do Q equals MC delta T for water in your calorimeter, you can then use the exact same equation to solve for the metal that you put in it. But your web assignment tonight is going to be a mixture of this type of problem, so multi-step, and what you're going to be doing in the lab a little bit. Okay? So,